Section 4.5 يتكلم عن the dimension of a vector space. عندنا يبدأ section theorem 9. If a vector space V has a basis P from B1 until Bn, then any set in V containing more than n vectors must be linearly dependent. نحن أول شي قلنا في تعريف البيسز إنه البيسز لازم تتكون من linearly independent set. فإذا أنا أضفت one extra vector ذلك معناته أن الست راح يكون فيها إيش؟ يكون فيها فيكتور زيادة. فالفيكتور زيادة هذا راح يحول الست من linearly independent إلى linearly independent، لأنه هذه أصلا من الأساس على طول فيها pivot in each column. لما أنا أضيف فيكتور زيادة راح تتحول الست من linearly independent إلى linearly dependent. نفس الحالة هنا عندي theorem 10. If a vector space V has basis of n vectors, then every basis of V must consist of exactly n vectors. يعني إذا عندي vector space V أخذت منها basis والbasis فيها إيش؟ n vectors. إذا كل basis ثانية كل ما أخذ basis لازم تكون consist of exactly n vectors. كل basis موجودة inside الvector space راح تتكون من n vectors. بعدين أخذنا اللي هو dimensional space. So definition: if V is spanned by a finite set, then V is said to be a finite dimensional. إذا كانت ال V فيها countable number of vectors, so that we said it is a finite dimensional. Dimension of V written as V. إذا هي عدد ال vectors اللي موجودة inside ال span, inside اللي هي span of V. So diamond V is the number of vectors in the basis for V. كيف أحدد اللي هي dimension of V؟ أحددها عن طريق numbers of vector اللي موجودات في البيسز. Dimension of the zero vector space zero is defined to be zero، لأنه هنا ما يعني لما يكون عندي zero vector إذا ما فيها عدد اللي هي ما فيها bases، إذا معناته على طول عدد الفيكتور اللي موجودات في البيس عبارة عن zero. That's why it is said here it is zero. If V is not spanned by a finite set, then V is said to be infinite dimensional. إذا ال V ما أقدر أكتبها بصفة span of vectors إذا بقول على طول it is infinite dimensional. إذا ال dimension هو يمثل لي عدد ال vectors اللي موجودات inside ال bases. فمثلا لما يعطينا هنا W is a span of these two vectors V1 و V2, show that dimension of W is equal to. إذا معناته we have to show that إنه ال bases contain two vectors. إذا عدد الفيكتور اللي موجودات في البيس عبارة عن 2 فيكتور إذن على طول this one is a basis. نفس الحالة في الباقي كله لازم نجيب البيسز بعدها نقرر هل هي نقرر إيش هو الدايمنشن. Classify the subspace of R3 by their dimension. في عندي 0 dimension، عندي 1 dimension، 2 dimension، 3 dimension. الكلاسيفيكيشن موجودات في الكتاب. آخر شيء theorem هنا 11. Let H be a subspace of a finite dimensional vector space V. Any linearly independent set in H can be expanded if necessary if a basis for H a basis for H. So also H is a finite dimensional and dimension of H is less than or equal dimension of V. يعني أنا إذا كانت عندي ال H عبارة عن subspace of finite dimension V، إذا الدايمنشن تبع ال H اللي هي number of linearly independent set in the basis should be less than or equal to the dimension of V. لأن أصلا ال V هي عبارة عن vector space، ال H عبارة عن subspace منها، فمن الطبيعي إنه البيسز لل V راح يكون عدد ال vectors inside vector of basis of V أكبر من أو يساوي عدد dimension of vector in the basis of ال H. Last theorem is theorem 12. Let V be a b-dimensional vector space be greater than or equal to 1. Any linearly independent set of exactly b elements in V automatically a basis for V. إذا عندي ال V with a b-dimensional إذا معناته الدايمنشن هنا ماله finite. لما آخذ الست which is linearly independent هذه الست فيها n اللي هي b elements نفس الدايمنشن of V إذا على طول أقول this one is a basis for V. اللي هي نفس الثيرم اللي قبل. إذا كانت أنا عندي ال V with b-dimensional vector space إذا any linearly independent set اللي فيها b elements على طول it is إيش؟ a basis for V. Part 2 any set of exactly b elements that spans V automatically a basis for V. نفس الحالة لما آخذ b elements that span V على طول this one is a basis. إذا this one ما يحتاج proof. كل ما أخذ set تنطبق عليها 1 or 2 so it is a basis directly. The dimension of null A and call A, the dimension of null A is the number of free variables. إذا لما أريد أحدد dimension of null A على طول أحسب كم free variables so that's represent the dimension of null A. Dimension of call A is the number of pivot columns. إذا dimension of null A لما أريد أجيب dimension of null A وهنا dimension of call A. This one is number of free variables. And this one is number of pivot column. فلما تكون عندي ماتريكس إذا لازم أول شيء أخليها في الإشيلون فورم. بعد ما خليتها في الإشيلون فورم أشوف كم pivot column إذا يمثل لي الدايمنشن of call A. كم عدد الفري variable إذا يمثل لي dimension of null A. For each subspace in exercise 1 to 8, A, find the basis, B, state the dimension. So the basis is the set of the linearly independent where they are coincide with H itself. So here if we say this one is H, so H can be represented as H is equal span of, since here we have two variables, so we will take the coefficient of S1 then the coefficients of T. So the coefficient of S is 1, 1, 0 and the coefficient of T is 2, 1, 3. So this H can be represented as a span of 1, 1, 0, 2, 1, 3. Since this one is not a multiple of this one, so none of these two vectors is a multiple of the other, so they are linearly independent. And since they coincide with H is itself, so the basis of H is equal, so the basis for H is equal 1, 1, 0, 2, 1, 3. And the dimension of H is equal to, since we have two vectors in the basis, so dim of H is equal to. We'll do the same thing for 3. So 3, if we said H is equal span of the vector, we have 3 vectors here since we have 3 variables A, B, C. So the first vector for the coefficients of A, we have 0, 1, 0, 1. Then the coefficients of B, 0, minus 1, 1, 2. Then the coefficients of C is 2, then 0, then minus 3, then 0. So H can be represented as a span of these 3 vectors. If we do row operation for this set, we'll find that we have a pivot in each column. So that means the set is linearly independent. So we cannot say directly this set is linearly independent. You need to check this one. So after you do row operation, you find that this set has a pivot in each column. So that means the set is linearly independent. And because it is coincide with H itself, so the basis for H is this vector, and this vector. So the set is linearly independent. You have to show this one by the row operation. It's linearly independent. So the basis for H is equal, if we say this one V1, V2, V3 is equal V1, V2, V3. Now since we have 3 vectors in H, so that's mean dimension of H is equal 3. So now let us do 5. So for 5 we can represent H is equal. So H is equal, also we'll take the coefficients of A, B and C. So now the coefficients of A, 1, 2, minus 1, minus 3. So it is equal span, sorry. Then the coefficients of B, minus 4, 5, 0, 7. The coefficients of C, minus 2, minus 4, 2, 6. We need to know if this set is linearly independent. If it is linearly independent, that's mean this set is a basis for H. So if we do row operation for the matrix, doing row operation for the matrix, if we say the matrix is 1, 2, minus 1, minus 3, minus 4, 5, 0, 7, minus 2, minus 4, 2, 6. So after doing row operation, we get the matrix 1, 0, 0, 0, then 0, 1, 0, 0, then minus 2, 0, 0, 0. We see here we have only 2 pivot columns. So the basis will be the first column and the second column from this matrix. So the basis for H is equal the first column 1, 2, minus 1, minus 3, because we need to take a set which is linearly independent, minus 4, 5, 0, 7. Since here we have a pivot just in the first column and the second column, so the basis for this one is the first and the second column. Since we have 2 vectors inside the basis, so the dimension of H is equal to. In 7 also we need to find the basis for this and then to find what is the dimension. So if we assume this one also H, so 7, so H will be equal to, this one is A minus 3B plus C is equal to 0, then P minus 2C is equal to 0, 2B minus C is equal to 0. So this is a homogeneous system. If we write the matrix of this one, for example A, this one is A, not H. So the matrix for this subspace is the coefficient of A, then coefficient of B, C, and then we have the column of 0. So 1, minus 3, 1, 0, 1, minus 2, 0, 2, minus 1, and here we have it is equal to 0. We need to do row operation for this one to know what is the basis. So it will give us 1, 0, 0, 0, 1, 0, then 0, 0, 1, and here we have 0, 0, 0. So after doing row operation, we say here the dimension of H is equal to null A, which is equal to the 0 because there is no free variable here. So from here we conclude that dimension of H is equal to 0. Because this one a homogeneous system, and then to find the basis for the homogeneous system, just we need to find the null A, a basis for null A. Since the basis for null A is equal to 0, that means the dimension will be equal to 0. Then for 9, find the dimension of the subspace of all vectors in R3 whose first and third entries are equal. So any subspace of all vectors in R3, this will where the first and third entries are equal can be represented as, if we assume the first entry is B, the first entry is A, the second is B. Since the first and the third the same, so this one should be also A, where A, P are in R. So now if we want to find what is the basis of this one, so this one is equal span of the first vector, the first variable. Here we have A, so the coefficient of A 1, then 0, 1. Then we have the second variable B, the coefficient of B is 0, 1, 0. So H is equal span 1, 0, 1, 0, 1, 0. Both of them are not a multiple of the other, so 1, 0, 1 is not a multiple of 0, 1, 0. So these two vectors are linearly independent. So the set is linearly independent. So the basis for H is equal these two vectors 1, 0, 1 and 0, 1, 0. So now the dimension of H should be equal to, since we have two vectors in the base. In 11, find the dimension of the subspace spanned by the given vectors. So we need to find first the basis. So in 11, our matrix will be 1, 0, 2, 3, 1, 1, 9, 4, minus 2, minus 7, minus 3, 1. We need to put this one in echelon form. So after reducing this matrix, we get 1, 0, 0, then 0, 1, 0, then minus 3, 4, 0, 2, minus 3, 0. So now this set has two pivots, which is in the first column and the second column. So this set is spanned by the two vectors of the free variables. We have two free variables, which is x3 and x4. So this set is spanned by only two vectors. So that's mean the dimension. So the dimension of H should be equal to, since we have two pivots. So the set in the basis will be only of two vectors. That's mean the dimension of H also equal to 2. In 13, determine the dimension of null A and call A for the matrices shown in exercise 13 to 18. So to know the dimension of null A, that's mean the number of free variables. The dimension of call A, the number of pivot column. So this is number of free variables. This one is the number of pivot columns. So in 13, the number of pivot columns, we have pivot in the first one, in the second one, in the third one. So the dimension of call A is equal to 3. Then the dimension of null A is the number of free variables, which is, we have this one free variable, this one free variable, so it is equal to. Now for 15, we have pivot in the first column, we have pivot in the third column, so dimension of call A is equal to. Now to find dimension of null A, which is the number of free variable, we have this one is free, this one is free also, so it is equal to. So the dimension of call A is equal to, dimension of null A is equal also to. Similarly, in 17, to find the dimension of call A, which is the number of pivot column, here we have a 3. So dimension of call A is equal to 3, and the dimension of null A is the number of free variable. Since we don't have free variable, so this one is equal to 0. Now in 19 and 20, V is a vector space. Mark each statement true or false, justify each answer. A, the number of pivot columns of a matrix equals the dimension of its column space. This one is true because the number of pivot columns always represent the dimension of column space of the matrix. So this one is true. Then B, a plane in R3 is a two-dimensional subspace of R3. A plane in R3 is a two-dimensional subspace of R3. This one is false because R3 should be two-dimensional because the plane must pass through the origin to be a two-dimensional. So this one is B is false. So the plane must pass through the origin. So that's we conclude it is a two-dimensional. Now for C, the dimension of the vector space P4 is 4. This one is false because we said it is coincide with R5. So this one cannot be, the dimension cannot be, it is not 4, it should be 5. So the set S must also have, sorry, the dimension of Bn is equal n plus 1. Sorry, the dimension of Pn is equal n plus 1. So this one is 5, not 4. If dimension of V is equal n and S is linearly independent set in V, then S is a basis for V. This is from theorem 12. First, the set should contain n linearly independent set, so then we can conclude that it is a basis for V. But here it said that if S is any linearly independent set, then it is a basis. No, we can say and S is a linearly independent set with n vectors, then we can conclude it is a basis. So this one is false. S must contain n vectors. Now for E, if the set from V1 to Vb spans a finite dimensional vector space V, and if T is a set of more than P vectors in V, then T is linearly dependent. So here we have this set is a finite dimensional vector space with B vectors, and T is a set of more than B. So then T is linearly dependent. This one is a true from theorem. Sorry, E is true from theorem 9. Now for 20, R2 is a two-dimensional subspace of R3. This one is false because R2 is not a subset of R3. So A false, R2 is not a subset of R3. B, the number of variables in the equation x is equal to 0 equals the dimension of null A. This one is false. It should say here number of 3 variables, not the number of variables. So we need to add number of 3 variables. So add here 3 variables. Then C, a vector space is infinite dimensional if it is spanned by infinite set. So a vector space is infinite dimensional if it is spanned by infinite set. This one is false. So because the basis could have a finite elements, so that's mean it is which would make the vector space finite dimension. The vector space finite dimensional. Then D, if dimension of V is equal n, and if S span V, then S is a basis for V. This one is, here it is missing that the set should contain also n vectors. So D is false. S must also have n elements. This is by theorem 12. Then D, the only three-dimensional subspace of R3 is R3 itself. So this one, true. So the coefficient will take the coefficient of the first one. Here we have 1. So that means the coefficient of this one is 1. The coefficient of t is 0. Coefficient of t squared 0. Coefficient of t cubed is 0. For the second one is 2t. So that means the constant 0. Coefficient of t is 2. Coefficient of t squared 0. Coefficient of t cubed 0. Now for the third one, minus 2 plus 4t squared. So this is minus 2, 0, then 4, then 0. Now for the last one, we have 0, then minus 12, then 0, then 8. So if we see this one, it is in echelon form, where we have here a pivot, then we have a pivot, then we have a pivot, then also we have a pivot. So from here we conclude that these columns are linearly independent, and so this polynomial or these Hermite polynomials are linearly independent in B3. So since we have a pivot in each column, so the columns are linearly independent. The columns are linearly independent, so H or this one can be written as a linearly independent MB3. So if we say this one is H, so H is linearly independent in B3. So now the dimension will be dimension of H or dimension of B3 is equal to, the dimension is equal R plus 1, n plus 1. So here it is equal to 4 since we have 4 linearly independent. So the basis theorem states that the Hermite polynomials form a basis for B3. So by basis theorem, the Hermite polynomial, the given Hermite polynomial form a basis for P3. In 23, let B be the basis of P3 consisting of the Hermite polynomials in exercise 21, and let Bt is equal 7 minus 12t minus 8t square plus 12t cube. Find the coordinate vector of P relative to the basis B. So we know that the Hermite polynomial is of these four. So if this one is inside Hermite polynomials, that means it is a linear combination of these polynomials. So we want to find the coordinate vector of this. So that means if we have Bt is equal 7 minus 12t minus 8t square plus 12t cube, that means we need to find the coordinate that make linear combination of this one is equal to this one. So this one is equal to a0 multiplied by 1 plus a1 multiplied by 2t plus a2 multiplied by minus 2 plus 4t square plus a3 multiplied by minus 12t plus 8t cube. So now we need to compare between the coefficients of this polynomial and this one. First we have the constant here 7, the constant here a0 multiplied by 1. There is no constant. Here we have minus 2a2 and there is no constant. So from here 7 is equal a0 minus 2a2. Now the second one will see the coefficient of t. Here we have minus 12, it is equal to, here we have 2a1. Then we have here minus 12a3. Then we'll see the coefficient of t square. Here we have minus 8. Then this one is for t. So for t we take 2a1, so this one should be in green, so that we don't confuse. So now for the coefficient of t square, here we have 4a2. Then we have, there is no one here. Then last one is the coefficient of t cubed. So here we have 12, it is equal to, then t cube we have here, this one is 8a3. So from here we can say that a3 is equal 12 over 8, which is if we divide it by 4 we get 3 over 2. Then for this one a2 will be equal minus 8 over 4, which is equal minus 2. For this one, if we solve it for a1, since a3 is here, so a1 will be equal minus 12 plus 12 multiplied by 3 over 2, and we divide all by 2. From here it is 18, so minus 12 plus 18 divided by 2, this one is 3. Then for this one we need to solve it for a0, so a0 is equal 7 plus 2a2, which is minus 2, is equal to 3. So now the coordinate vector of B is a0, a1, a2, which is a3, which is 3, 3, minus 2, 3 over 2. In 24, let be the basis of P2 consisting of the first three Lagrange polynomials listed in exercise 22. So then, and let Bt is equal 7 minus 8t plus 3t square. Find the coordinate vector of P relative to the basis B. So again, we'll do the same thing we did in 23. So 24, our Bt is equal to 7 minus 8t plus 3t square. This one should equal, it will be inside the linear combination of this one. So it is a0 multiplied by 1 plus a1 multiplied by 1 minus t plus a2 multiplied by 2 minus 4t plus t square plus a3 multiplied by 6 minus 18 t plus 9t square minus t cube. So again we need to solve this one to find what is the coordinate vector of B relative to these bases. So from here we say again, see the constant here we have, which is 7. So 7 is equal to a0 plus, here we have a1, here we have 2a2, then we have 6a3. Then for the coefficient of t, here we have minus 8. So minus 8 will be equal minus a1, then minus 4a2, then we have here minus 18a3. Then the coefficient of t square is 3, so 3 is equal, then from here we have a2, then from here we have 9a3. Then the last one we have, so last one is a3, so because here we have t power 3, so 0 is equal to a3. So from here, to solve this one and find what is the coordinate vector, so a3 is equal to 0. From here, a2 is equal to 3. From here, we need to solve it for minus a1, so we solve it for a1. So a1 is equal to 8 minus 4a2 minus 18a3. We know that a3 is equal to 0, a2 is equal to 3, so 4 multiplied by 3 is 12, 8 minus 12 is equal minus 4. And this one we need to solve it for a0, so a0 is equal 7 minus a1 minus 2a2 plus, sorry, minus 6a3. So a3 is 0, a2 is equal 3, so this is minus 6. Then a1 is equal minus 4, and here we have minus. So it will be 2, 7 plus 4 minus 6. This will give us 4 minus 6 will be equal minus 2. 7 minus 2 will be equal 5. So the coordinate vector of this one, P D is equal 5 minus 4 3 0. In 25, let S be a subset of n-dimensional vector space V, and suppose S contains fewer than n vectors. Explain why S cannot span V. Let us do this one by contradiction. We assume that S contains fewer than n vectors, then can we show that S is span V? So let us see that one. First of all, since S is a subset of n-dimensional vector space V, so that's mean n is greater than or equal to 1, because S cannot have fewer than one vector where V is not equal to 0, so n greater than or equal to 1. Let us write this one. since S cannot have fewer than one vector, because we said that the subset S, the S is a subset of n-dimensional vector space V. So if it is a subset, so that means it contains more than one vector at least one vector or more. So that's why we assume that n is greater than or equal to 1. Now let us assume that, so suppose we assume that S is span of V. So S is equal to span of V. So S has less than n vectors, because it says S be a subset of n vector space, and suppose S contains fewer than n vectors. So now S has less than n vectors. So by the spanning set theorem, spanning set theorem some subset let us say S prime. So some subset S prime or S dash of S is a basis for V. So first we assume that S is a span of V. So that means S has less than or equal to n vectors. If we take a subset from S, so by the spanning set theorem, this subset of S is a basis for V. So, and this subset, this subset of S, that means S dash contains fewer than n vector. So now this subset contains less than n vectors. That means there exists a basis. So there exists a basis S dash for V with fewer than n vectors. But this is impossible by theorem 10, because theorem 10 says that any set of n, any set spanned by V with n vectors, it should be a basis. But here we have this set is less than n vectors, so this is impossible by theorem 10, but this is impossible by theorem 10, since dimension of V is equal to n, thus S cannot be span V. S cannot span V. Span the vector V, so here let us write span.